Hello friends, I am Saroj Vishwas, gold medalist, first rank holder of 1994 batch in engineering stream of all the colleges affiliated to University of Mysore during that period. A BE in civil engineering from National Institute of Engineering Mysore, a MTech in structural engineering from Indian Institute of Technology, Delhi, that is IIT Delhi, a Sun certified Java programmer, Sun Microsystem USA. I have more than 25 years of professional experience in designing building structures and allied subsidiaries. I invite you all to learn with me how to design building structures using commercially available structural softwares with the help of some manual computation as and when needed.
Today's tutorial we shall learn design of hinge base plate or the pin base plate, and then we shall learn design of rigid connection, that is beam to column connections. And before that I would like to go back to the topic of the last tutorial in which I had discussed design of base plate having 5 anchor bolt about one of the flange. So you can see in this figure there are 5 bolts around about one flange. So obviously there will be some eccentricity. The CG of this bolt group lies at this black point. So this is around distance D from the center of the flange of the I section. So this will create additional movement about the bolt group. So how do we take into account of this bolt? Account of this movement. You see, this on the left hand side there are 2 bolts, on the right hand side there are 3 bolts. So the CG of the bolt groups lies here. The tension because of the movement or direct tension is mainly through the flanges. So tension is through the flanges. So tension is acting here. This T shine designates the tension. So now we can replace this tension by applying this tension about the CG of the bolt group and plus a moment. That moment will be M is equal to E into D. D is the distance between the CG of the bolt group and the actual tension through the center of the flange of the I section. So knowing H1 and H2, we can calculate what is the additional tension that will be created in this bolt, and this tension has to be added to the actual tension developed due to the structural forces taken from the structural analysis. So whenever for this type of 5 groups of bolt, it might not be considerable, but when there is a huge load and bolt group spreads over, this could be considerable, and we should always take into account eccentricity of this CG of the bolt groups while designing the base plate. Now let us come back to the STAAD file. This is our STAAD file. This is the pin joint. Here is the pin joint, if you see. So first of all, we shall design a base plate for this pin joint. This is an Excel sheet which has been developed to design a pin joint. So this has been given in my website. So you can download it from there. Now if you see, the anchor bolts lies within the flanges. So it could be two numbers of anchor bolt, or it could be 3 numbers of anchor bolt. If the column size is huge, we usually provide more than 2 numbers of anchor bolts, so that to have compatibility with the sections. So let us first rename the connections, which shall be base plate 2. Let us name it base plate 2, and it shall be at the intersection of, let us see at which intersection it is in there. It is at grid D, this is grid D, and this is grid 2. So it is at intersection of grid 2, D and 2. So let us write as intersection of grid at intersection of grid D and 2. Now we might not record these forces. Let us delete. We shall take these forces from the start file. So let us go to the start file. Now mode, post processing, apply, report, support reaction. Here we shall record only the force oil. We shall record the, if there is any kind of uplift is there, then we have to take that into consideration. So let us see. So this is the reactions. So we do not require reaction for the all the load combination. So report, support reactions, force oil, loading. You have to consider only 51 to 338. Now, so copy. Let us take this to the Excel file. We do not record. Let us delete all of this, whatever it is there. Now let us paste it here. So this is our maximum pressure, and this is our Y. This is our Y. Let's mark it. So there is no uplift, so we do not require to design for uplift here. So to match whatever we have got from the start file reaction, the Excel sheet was prepared with respect to a beam forces. So we can use that with some little tweaking. So our axial force for these cases remains maximum compression 40. So and load case is 50 on, that is okay. Load case is 50 on. Bar as well. So this is our shear Y. Here will be shear Z, that those are all 0, so no problem. For here again, for the lower forces, we can take it force Z, shear Y shall be the force Z. So this shall be 23 and shear Z shall be 46, so that is 0. So you shall require some kind of tweaking to use this Excel sheet. See, I provided two numbers of columns here because at times we might have to take support reaction from two columns and combine them together. So in the third rows, the combined reaction value will come. So we need not to compute it manually. Now let us see the sizes of the column. Property, this is 300, so 300 by 5, and then flanges are 150 by 8. So the change is 300 by 5 and 150 by 8. Now supporting beam, we do not have any supporting beam, so let us keep it like this only. Now base plate size works out to be 326 mm and width of the plate is 160 mm. So 150 plus 1010. So now let us see. See, there is no tension, but we shall treat this as tension just to showcase just to showcase how to design when there will be axial tension. So this axial tension has been taken. Actually there is no axial tension. We should have put these things as 0 here, but just to show I am keeping it like that. This is not actual tension, but only to showcase the design of under axial tension. I am keeping it. So we shall use only 2 numbers of bolt. The figure it is shown 3 numbers, but we are using 2 numbers. So that is why the only distance of 150 is being shown here. So let us use a thickness of base plate thickness. Let us try 12 mm. Let's see what happens. Okay. Now before that we need to see the pressure. What is the pressure if this pressure is being exceeded in case of bearing pressure of concrete. So let us change this bearing to concrete. So allowable bearing pressure is 11.25. You have to see the relevant sections of bearing pressure in the IS 800 2007. Or here we have used the variable bearing pressure from this is the bearing pressure that has been taken from IS 456.45 FCK. So we need to tweak this Excel sheet as per requirement, because it has been developed both for a column that can arise from complete, or from a stub column that could arise that could be supported on a beam. So these are some cases which are developed, which has been provided to take the cases of beam coming out for a column, a stub column coming out from a beam. So our case, this is not required. Next, we shall see the design of a moment connection. This is one of the sheet that has been developed for design of moment connection. So we have to again change these locations. So let us go back to the STAAD file. We have these members: ship B, 52, 50, 108, and these are similar members, I suppose. R13, both are R13. So this is a moment connection. If you see the 3D, that's a moment connection coming out from the column. It's a column beam connection. So we shall read the maximum bending moment from here. So this is our beam 50, 52, 113 and 108. So let us name this end plate 1, EP1, 50, members covers us 50, 52, 103 and 113. So we have to take new forces. So let us see. Mode, post processing, report, beam end forces, maximum moment, loading, 51 to 338. So let us take these forces to the Excel sheet. Paste. So this is 129. We have to see the lowest part also. At the lowest part, it is 98.86. So our governing moment is 129 kilonewton meter. So let us take this forces here. Beam 50. Okay. Now you have to see whether this axial force is compressive or tension. So let us go to the STAAD file. This is our beam 50. Selected view, load case 50 on. Let us. So this is the tensile force under load case 50 on. So in the Excel sheet we have to change it. It's tension. So this will be added. So now let us change the size of the beam. What is the size of the beam? 350 by 5, 175 by 10. 350 by 5, 175 by 10. And then we have to check the column also. View, whole structure. Let us put up the shear diagram. So our column is again 350 by 5, 175. Column is also same. 350 by 5 and 175 by 10. So this local wave thickness, as of now we are keeping keeping it 5. So at the connection point, at times we might require to increase the thickness of the web. So let us take bolt diameter as 20. So our size is swapped out to be this. So 8 bolts. So now let us go to the forces. So thickness of the plate shall be required more. So let us go back to the Excel sheet where the thickness of the plate has been provided. So let us make it 20. So this is our prying forces requirement. So it is satisfied now. 16.7 mm is required for prying for to now see tension capacity of the bolt we have chosen is 141, but tension so 20 mm, so we have to increase the bolt sizes. So let us increase it to 24. Okay. So plate thickness of the bolts from the prying force concentration. Now it is safe. It is safe now. Then we have to check the shear interaction. Then we have to check column wave local yield capacity. Then column wave coupling. Then so size of the weld for stiffener required shall be more. So what is the stiffener size we are providing? We have to see. From design calculation, the stiffener thickness of stud will be 10 mm. So we can easily provide a size of 8 mm. So let us check with a size of 8 mm. What is the size we have taken? Weld sizes. So column to stiffener to the flange of the column. This we are making it 8 mm. So see this, it is depending for local increase of web thickness. So let us go back to the top again. So let us make it 6 mm. Local web thickness at connection TWC. So now web thickness is safe. Optionally, we can provide diagonal stiffener, but at floor level we will not be able to provide the diagonal stiffener. But at raptor level, we can provide diagonal stiffener. But that depends on how much space is available. So this connection design is over. So wherever there is a movement connection, we can design in the same way. This raptor to column movement connections we can design in the same way. You have to take the section sizes at the connection itself. So here it is 350 by 5 and 150 by 10 at connection. So raptor to column connection will be, the sizes has to be at the section sizes has to be at whatever there is at the section, at the joint itself. So with this we finish design of connection design of rigid connection or movement connection or fixed connection between beam and column or beam, column and raptor. So in next tutorial we shall try to cover the design of shear connection and then design of connection design of studs, and additionally we shall try to cover the connection design of bracing as well.